Assalamualaikum and good morning to Prof. Shamsul. Today we are from Group 11. Want to present the process and plan design. We have a topic of production of cumene from benzene, and as the topic suggests, our feedstock is using benzene to produce 100 tons per year of cumene with the purity of 99.5%. So this is our group members, which is Aizzudin, myself, Hedaya, Rishi, as well as Aisyah. And for the table of content, so we will look into a process overview, main reaction, PFD and PFD, and the overall mass balance, waste system control, elements process as well. And we will also look into material properties, a little bit of the equipment list and the heat usage. So process overview. So alkylation of benzene and propylene is the most used process to produce cumene, which involves the reaction of benzene and propylene over a catalyst. And our catalyst is zeolite catalyst. So the advantage of using this zeolite catalyst in the process is less needing for regeneration, which means that the process can run for months without worrying about affecting the selectivity. Second one is no corrosions to the plant and more profitable in terms of the capital cost as well as the operating costs, since the temperature required is lower, which can also increase the shelf life of the reactors. And as you can see here, our feed is benzene, so we put in about 12,883 kilogram per hour of benzene with 6,000, almost 7,000 kilogram per hour of propylene, as well as 300, a little bit of propane. And with the help of zeolite catalyst, we are able to, with our cumene plant, we are able to produce a purity of 99.5% of cumene, which amount of 19,701 kilogram per hour. And our target production is actually just 11,415 kilogram per hour. So this is sufficient. And the IPB is at 172 and propane is 304 kilogram per hour.
Hey guys, now I will be explaining about main chemical reaction involved in cumene production from benzene. The first reaction will be alkylation of benzene with propylene to produce cumene. This is the most common route for industrial scale cumene production. This is the main reaction, and it is also irreversible and exothermic reaction. Once cumene is produced, it can further alkylate to diisopropylbenzene, DIPB, as a side product. This will be the side reaction. So cumene will react with propylene to produce DIPB. Next, the final reaction will be transalkylation reaction. So the unwanted diisopropylbenzene is converted back to cumene while transalkylation with benzene. All reactions are okay in liquid phase. So these are the main chemical reaction mechanism for alkylation and transalkylation. From the manual calculation, the reaction yield of cumene is 17.33%, while for the diisopropylbenzene, we got 6.67% of yield percentage. For our product specification, the purity of cumene will be 99.5%, and the concentration of diisopropylbenzene will be less than 0.5%. The overall yield percentage is 99%. So this is the block flow diagram for our plant design. So the fresh feed, which consists of benzene and propylene, will enter the alkylation reactor to undergo the alkylation process. After that, it undergoes several of separation process in order to get high purity of cumene. The unwanted DIPB and extra benzene will be recycled back to the transalkylation unit to produce additional cumene. So this is the process flow diagram for our plant design. So the main unit will be alkylation reactor R1, transalkylation reactor R2, and there will be 3 distillation columns, which are C1 depronizer, C2 benzene column, and C3 cumene column. So this process requires 2 reactors, 2 distillation column, a depronizer, pump, heat exchanger, cooler, heater, and valve. So that's all from me. Thank you.
For the overall mass balance, we first list out the specification that given from the assignment, where the purity of the CUMENE product should be 99.5% and the outlet product should be 175 kiloton per year. And then from journals, we found the propylene to propane inlet percentage is 96:4. Using this information, we find first the degree of freedom, where the number of components is 5, number of specification is 3, and number of atomic species is 2. adding up these members together, we find the degree of freedom is 0, which allows us to complete doing the mass balance of this process. We found out the inlet of our feed, which is propylene, benzene, and propane, as listed in the table below, and we use the specification to find out our final outlet. From our process, we assume that we have some waste from feed and byproduct system. So we followed few approaches that will help us to avoid this waste. From the first approach, which is we use it as a fuel for process heaters, and that because it have a high amount of heating value, so the waste stream would be burned in a process heater working in 99% removal in order to compute the controlled emission of CUMENE. And the second approach, we are raising the temperature of the reactor inlet stream, and we are changing the reactor size, which will make the conversion is higher. Finally, we can change the benzene recycling to the feed section in an effort to eliminate such raw material waste. In this case, we are recycling the unreacted material. And from the byproduct that we are getting from this process, which is the only product, is propane. So here are some methods to recover propane gas byproduct. First method is utilized for energy generation, so we can generate heat or power from propane, and so we can capture it before it released into sky. And second method is feedstock for the production of propylene. Propylene may be produced from propane using a technique called propane dehydrogenation, which is PDH. Finally, vapor recovery units, which are a system for compressing smaller volume gas streams that will collect and injected into the section of a bigger compressor, meter one, site-specific fuel gas system, or straight into the collection line. For our process, we use the X-Max process method.
My name is Siti Binti Isham. So I will start with the raw material storage. The reactants for the process are fresh propylene with 96% of propylene and 4% of propane, and also fresh benzene. The feedstock is stored at 25 degrees Celsius and 1 bar. The first main unit is reactor 1, which is an alkylation reactor. There are two reactions involved in this reactor. The main reaction is the desired reaction, alkylation of benzene and propylene to produce CUMENE, and the other one is the side reaction for the production of the IPB. The design specification for this reactor is the inlet temperature between 150 to 200 degrees Celsius. As you can see, the inlet temperature in Excel is 170 degrees Celsius. However, in Aspen, the inlet temperature is 101.93 degrees Celsius. The outlet temperature is the same for both Excel and Aspen with 257 degrees Celsius. The reaction is non-isothermal. Next, the pressure is kept high at 30 bar to maintain the liquid state inside the reactor. Benzene to propylene ratio is 5:1. As you can see in the inlet of the Excel calculation, the mole fraction has been calculated with this 5:1 ratio because we have benzene recycle stream going to the reactor. The propylene conversion is complete conversion. As you can see for Excel calculation, the outlet propylene is 0, while Aspen is nearly 0 propylene. The effluent mainly contains benzene, CUMENE, DIPB, and propane. As you can see, the values for the production of CUMENE and the IPB are the same for both Excel and Aspen. However, in Aspen simulation, there are large deviation for benzene and propane flow rate. This is because supposedly propane is being completely removed in the depropanizer unit. However, there is still a major amount of propane being recycled in the benzene recycle stream. This deviation from Aspen simulation should be further investigated. Maybe the temperature or pressure or any other condition affects the distribution in certain unit. This is the reaction kinetic information that we extract from the journal. This information is used in the Aspen simulation for the reactor units. This information might be useful when doing the reactor design for next semester. Next, the catalyst used in the reactor is zeolite catalyst because it is less problematic in terms of corrosion and separation as compared to phosphoric acid and aluminum chloride catalyst.
The main function of depropanizer is to separate propane from the feed. This is because the fresh feed propylene consists a little amount of propane which does not involve in CUMENE production. So this depropanizer runs at 111 degrees Celsius and 1 bar in pressure. This separation unit is going to receive the effluent from the alkylation reactor, which is stream 8, and it will nearly separate all the propane as an overhead product and purge out. This refers to stream 9. So the bottom product, which mainly consists of CUMENE, diisopropyl and benzene, we move to the benzene column. So these are the results we get from Excel calculation and Aspen simulation. Both result is different with each other. This is because several assumptions were made on this unit and other unit, such as alkylation reactor. So for this unit, all the propane were separated as a overall product were assumed, while in Aspen simulation, there are little amount of propane left in bottom product.
Next is the benzene column, which is a distillation column that get a mix stream from the transcalation reactor and the depropanizer that will be sent to the separator column. In the top, we have the benzene separated by this column before being recycled to the two reactor, and in the bottom we have CUMENE and DIPB. The specification and condition of this column is temperature 86, pressure is 1 bar, inlet compounds will be benzene, CUMENE, and DIPB, and the function we have to separate the benzene from the feed. Using the parameters are listed in the tables in this side, we found out the design specification should be minimum number of stages is 8, and the feed inlet stage is 4, and reflex ratio is 0.24. In this slide, we can show you the manual calculation that did by Excel and the Aspen calculation.
So moving on to the fifth stage, which is purification. So it starts off at the CUMENE column. So the CUMENE column plays an important role for our production process. Its purpose is to separate CUMENE as an overhead product, which contains a high level of purity, at least 99.5% that we desire. So at the bottom, there's a lot of DIPB that are going to the recycle stream. So the specification and conditions for this is the temperature is it must work at 155 degrees Celsius, the pressure at 1 bar, and the number of stages that we calculated is equals to 11, and the feed will enter at stage 4. So this here are our manual calculation as well as Aspen calculation. So if you can see, the value for the mass balance overall is not much different between these two calculations. However, there is a bit slack on the components, because in the manual calculation we assume that the benzene, propylene, and propane is equals to 0 in the inlet of the CUMENE column. However, in this Aspen calculation, it is not 0, so there is a little trace of benzene, propylene, and propane, so it affected a bit of our calculation. However, we still get what we want to have, which is the CUMENE at the top at the overhead product. Still a lot, if you can see here, is about 17,281 kg per hour. And the next stage is recycle of unreacted material, which starts off at the transalkylation reactor. So the transalkylation reactor is a critical component in our plant, as it serves as a way of increasing the selectivity for CUMENE production, and it achieves this by converting the undesired product DIPB, because from here before, the DIPB here will go into the recycle stream, which also contains benzene, and we will mix with benzene and DIPB will go into the transalkylation reactor. So our transalkylation reactor is configured as an adiabatic reactor, which means that there is no external heat exchange occurs during the reaction. So the temperature the reactor operates at 220 degrees Celsius and the pressure of 30 bar. And these conditions have been carefully selected based from literature resources, and it is important to maintain the temperature within that range of 200 to 250 to ensure the optimal kinetic reactions and as well as the selectivity. And the catalyst that we use in this calculation reactor is called beta zeolite. So for the next one, this is the manual calculation and the Aspen calculation. So the same case as before, we assume that in the transalkylation reactor only has benzene as well as the IPB. However, in Aspen calculation, there is also another elements which are CUMENE, and which we also have propylene and propane in the transalkylation reactor, which affected slight a bit of our calculation. However, in terms of the mass balance, it is still considered acceptable.
This is the draft of equipment list involved in the process for now. We have 4 pumps, 4 heat exchangers, 2 condensers, 2 reboilers, 2 reactors, a column, and 2 distillation columns. The detailed equipment design and sizing will be continued for next semester. Next, this is the heat usage for the main units calculated from Excel. For the alkylation reactor, negative value in a chemical reaction indicates that the reaction is releasing heat to surroundings, as it is an exothermic reaction. Next, this is the reference journal that we refer to. That's all from us, Group 11. Thank you.